Hello and welcome to our today's online training for students. My name is Jürgen Teilmann and I've been working for Dlubal Software now for the past 2.25 years. I work mainly in customer support, so I handle all kinds of questions from you, our customers. And today I will be your host and presenter for our students online training. By my side is my dear colleague Rebecca. Rebecca, you have the field to introduce yourself.
Yeah, hi, my name is Rebecca Göbe and I work at Dlubal Software since 1 year now. And I work in customer support also, but also in the development for web service and API. And today I will answer your questions.
Thank you very much, Rebecca. So she just told you she will answer your questions. Now you can see our names here, and I will show you the go-to panel. And in order so you can see the full screen, we will deactivate our webcams now. So for today, we will be using our GoToWebinar platform. I guess you are used to this now. If you can't see the panel, there's an orange pointer. Just click on that and the panel should show up. You can do a sound check and adjust your audio settings. And if you have any questions, just go to the section for the questions, edit your question and send it, and Rebecca will answer you as quick and good as possible. So now for our today's agenda. You have now been watching already 5 different trainings in the series, and now we're in the final part in my favorite section, and that's the introduction to our timber design add-on. So what do we do today? I have 4 small examples for you prepared, and I will show you some, well, maybe news or not so news. So before we start, I have one call of action to you. And this is, I send you a question. Have you already carried out timber design using structural analysis software? I start the poll and you can just click yes or no. Okay, all of you have voted. I close the poll and display the results. So the majority of you already have used structural analysis software for carrying out timber design. For the rest, don't worry. I give you the introduction to our timber design in RFEM, and maybe for the others who already have carried out this timber design using structural analysis software, maybe there's some differences to other softwares you might have used, or maybe you can still learn something new today. Good, I stop sharing the poll. Yeah, you should now see my PowerPoint again, and I switch to the RFEM. And I will start with a really, really simple model. I create a new one, and this will be a timber column for a stability check. Okay, I start with my project. I have a project on my PC called Introduction to Timber Design. This is where I want to save this model. And I call this number 1. Timber column. Okay, it will be a 3D model. And I need, since this is an introduction to the timber design, I need to activate the according add-on in the section add-ons. Next, I go to my standards, which are already set to Eurocode and the German National Annex. So now for timber design, there's something special. You need the standard group in Eurocode EN 1990 to set this to timber. That's because of regards to our serviceability limit state, I will show you later. And we leave it without any national annex because this is an international training. I change the other standards to CEN as well. Okay, that's all we need right now in our model base data. So I create this file. Okay, I have my working plane set to the global XY plane. And now I start with one member. I could set it via two nodes, but I choose another option. So I click on the drop out arrow, and then I set a single member perpendicular to my working plane. Then I get to the usual dialog you might know right now, new member. I say this is a beam member and I want to give it a section. This looks really good right now, but I think I just edit it just to see if it's the correct one. So it's not the correct one. This other one I don't need, so I delete it. This is just a carryover from a former model I used. So I want a rectangular cross section. That's okay. I could also use the library, but I'm already in the correct section. And the material is wrong. Just change that as well with the dialog edit. Delete the one I don't need. And then I go to my material library, go to the region, European Union, material type timber. And then I want softwood, C, and use the C24. Okay, so that's my material for this cross section. And now I need to edit the dimensions. So I go to parametric massive 1, and then I can edit my dimensions. So it's 160 millimeters in width and 200 millimeters in height. Say okay, and now I have my cross section defined. And you can also see that the material is now adjusted accordingly. I hit OK, and you see another dialog for the length of my member. I want this to be 4 meters long. And you see a little picture of my upcoming member, but it's showing downwards in the positive Z direction. So I want to flip it around, and I can use this in my dialog. There's a small button for flipping the orientation of this member, and then I can set it right on the I can set it right on the node where I wanted it to be, but somehow there's a problem with my GoToWebinar. I just set it to another node. Usually I could set it on the origin point of the coordinate system, but this hasn't worked out the day before yesterday. I guess there's a difficulty regarding our GoToWebinar software. So this is usually, if you do this, this will work just fine. I just select this column again and use my favorite tool, move and copy. I measure my displacement vector. And now I can capture the origin point of my coordinate system. So this is where I wanted the column to be. Just a little hint. Okay, now we have the column and we need some nodal supports. So I go to new nodal support. This one is hinged. Okay, I edit it just to give it another support around, so rotational around the global axis. Go to OK, assign it to the bottom. I hit apply and stay within the dialog so I can add a new support, which is just rotational around the x-axis, not around the z-axis, and translational in x direction. So you have a small picture on the right-hand side to see how this will look in the rendering. I hit OK, assign it to the top node of my column, and hit OK. Good. Now we need a load case. You can see the self-weight load case is already activated. I just edit it using the button for editing. Because I don't want to calculate the self-weight, I deactivate the self-weight and I make this one a design load. Okay, so this is all the forces I want to calculate are given as design loads in this example. This is a permanent load case, and we have our load duration. And this is the point why I told you we need to have the timber, the EN 1990/timber setting. I can go to base and I can also change the standard group for my combination wizard and classification within this dialog. And if I go back to my EN 1990, which would be set by default, I go to the load case and there's no possibility to enter the load duration. So I go back, like I told you, EN 1990/timber, say OK, and now I can edit the load duration and I set this one to medium term. Good. What I also want to do is I deactivate my combination wizard because I only want to use one load combination. So we have the load case. We need a design situation. For the stability check, we just need our ultimate limit state. So I delete the other ones. And the design situation is also active for the timber design. This usually happens by default, and sometimes you should check that too if you want to do a design situation for a certain add-on to have it activated in this section. Okay, I go to load combinations. Since I said I want to define them manually, I will do this right now. And using this little start button, I create a new load combination and go to assignment, and I assign my design load. Good, I say OK. Then I will define a nodal load. Program asks me which load case, which is pretty straightforward because we only have one right now. And I set my nodal load to the top of my column like this. And we need to apply a force, in my case, of 150 kilonewtons. We need a direction for that force, so I go to load type, coordinate system global in the Z direction, and this is the one I want. Otherwise, we could change the direction. Say OK, and the load gets applied. Okay, so I have all I need for a structural analysis of this column, and what I want to do now is assign the design properties. I go back to the dialog of my member with a double click. And you can see that we have several tabs I haven't shown you yet. We had section, now I go to the design types. And here we have effective length. So because in timber design, we normally work with our equivalent member method, we need to have effective lengths for the stability check. Right now, there's no one defined. I click on new effective length. and I can consider my effective lengths for several stability checks. I deactivate the lateral torsional buckling in my case because this is just a simple column and there would be no lateral torsional buckling. I wouldn't expect that to happen. You could have it activated, but in this case, I know this will only be prone to our compression and flexural buckling. I go to the next step where we set our nodal supports just for the effective length. So you know what I mean. On the right-hand side, there's a small bitmap, and you can always use this button. I circle my mouse around to go to the dynamic picture of your model. And so you can enter your supports according to your global nodal supports you have. So on the bottom part, these two directions are supported. This is correct. However, on the top, there's only support in one direction. That's the global x-axis. And if I check with my local coordinate system, that's also the local z-axis. So that's the one supported, and the local y-axis is not supported. This is why I deactivate this here. Okay, down we have our effective length factor. I just leave this to 1 and say okay. Whoops, that's too quick. In the design types, we also have our service classes. Now, what does this mean? You can edit the service class and you get a small example picture explaining what are the service classes: dry, moist, wet. I leave it to service class 1, which is dry. And yep, that's all for this example. I can run the calculation using the drop-down in this calculate button and say, please calculate my timber design. Okay, you can now see in the table down below, you have your design ratios on members. Design checks are fulfilled for the section proof and the stability check. You can also do a double click maybe on the stability check to get to the details of the design check. And then you have all the formulas the program uses, and you can do in a comparing calculation to check if your model does the right thing. So I go to my effective lengths and I say, okay, it's 4 meters and 4 meters. It's a bit strange to me. So I go to close and I go back to my member design types. I go to the effective lengths, to nodal supports, and I will check this one also with, there's another info button, which is the correct of my 4 typical Euler cases for buckling. And you might have seen already, since I've told you in detail that we don't have a support in the local y-axis, however, a rotational restraint down here, that in the y direction, this is not our Euler case from here. It's rather like a cantilever column. So I go to the y direction for our effective length factors, and I can choose right here, there's cantilever factor 2. I say okay. Yes, I want to delete the results because they have to be calculated new. And now you see that the stability check is no longer fulfilled, since now we have the correct effective length for this column and the stability check fails. Okay, so another thing I want to show you here is in the input data in the ultimate configurations. I go to member stability, and there is a stiffness reduction due to creeping. It's a reduction of stiffness with a coefficient, but that is according to DIN EN. So this is only applicable for the German national annex of Eurocode 5. So if you don't work with the German national annex, you can forget this. But if you sometimes have to work with the German national annex, there's a text. This creeping is comes into effect when you have service classes 2 and 3. So that's also something we haven't used in this example. But just that you have seen it once, that would be here. Okay, no, this time I don't want to delete my results. I save the model and I will go on with my second example of today. This is up here, number 2, design supports. So we have now a small flat roof, wall mounted on the left hand side, and there's a beam supporting this roof on the right hand side. And we have these pink little thingies here. This is about the design supports I will introduce now. These are predefined now, and just to let you know, the design supports have two main functions I want to show you today. The first one is they give you the boundary conditions for the design of the compression perpendicular to the grain direction. So this is like with these design supports, you define an area of where the load gets spread onto the beam or the member set. And the second one is you use those design supports for the segmentation of your members or your sets of members for the deflection design in SLS design checks. Okay, so now just to let you know what this model is about, I give you a small introduction to those different design supports I have. So we have underneath each of our nodal supports a design support, and the others are equal on top and bottom. So this is one on bottom of those guys here, and on the purlins, and the other one is on top of our lateral beam here. Good. I go to my member sets. Just want to have them visible, so I can click on the first member set. And in these additional tabs in the timber design, in the design properties, we can go to our effective lengths, but we don't need them here. And I go to my design supports. So we have, since we're now looking at this set of members, we have one at the beginning. This is, remember, where our wall-mounted nodal load is. We don't have any design support at the end of this set of members because this is a cantilever out there. And here where the lateral beam is mounted, you get the internal node support. Okay, and now I just edit the first one on the wall mounted side. I go to edit, and here you can see what you define within those design supports. So this is a support in the Z-axis. You can also add it to the Y-axis to have it in 2 directions. Just deactivate this again. This is just a vertical support. And you can define different length. The picture on the right-hand side shows you exactly what is meant by which parameter. So the length is given by 60 millimeters. That's just the default value. And the width of this design support can be given manually, or you just use the section of your member. This is what I want to use right now. You can also define this as an inner support or an outer support. So this is at the end of my member. And there's another factor for the compression perpendicular to grain. This is by default set to 1.5, and you can also use some of these suggestions. Okay, you can also say it's active for fire design and for the deflection design. Okay, same goes around for the second one. This is here. You can also edit it in the same way as the first one. I say okay. I have my load cases just to show you. There's one load case, just an arrow load to get some results. And I let the program calculate the timber design. Okay, so I go to my results, design ratios on member by member set. And now we just watch our member set 1. And now there is the section proof, there's the serviceability design checks. And I go to my SP 1400, also make a double click on it. You can see compression perpendicular to grain. We go to our details and you can see our design check on that. Somehow this is good. I would have expected it to be not fulfilled, so maybe there's something wrong with my input data. Let's see. Oh yeah, it was the wrong member. So this is on the lateral beam. We go to the details of that design check, and then you see it is not fulfilled. You can check the formulas, and sooner or later you will find, okay, this is due to a too small area of the load spread. And this can be simply edited just by making this design support a bit wider. So I go to my types for timber design. Nope, sorry. It's on the types for members. I have my design supports. And this is my design support 1, where I showed you 60 millimeters. So I spread this load over 80 millimeters. Say okay. But you still have to remember this need to fit your actual construction. You cannot just say, okay, I make this bigger and don't in the reality. Then you calculate. And yeah, again, add member number 2, compression perpendicular to grain is now fulfilled and governing for this design check. And you can see due to this spread over a wider area, we have a lower pressure on our grain, on our member. Good. What I want to show you next is when we go back to this set of members number 1, under design types, there's another possibility add those design supports that you can maybe add a notch for the member. So we have the local section reductions, and you can enter any section reductions you want. Go to a new local section reduction, and then you can have several notches. I make it a start notch. You have the picture on the right. Just to show you, it will start with a length of 4 centimeters. So that's 0.04 meters. We have it defined by the depth and have a reduction of depth by 100 millimeters. So that is H minus H effective. So it's the delta down here. This is 100 millimeters. It's on the plus z-axis of our member, so the bottom part, that's okay. And we have a notch at support. So this is also vital that we check this here. I say okay. Yes, we will delete the results, and now you have this notch also visualized in the picture, also in the model. If I say reduce the size of those nodal supports, you can see the notch in the rendering of the model. Calculate the timber design once more, and now just skip this error. This is something dealt with in our development. What I want to show you is the notch at support section proof, where you can also see notches in tension and your design check for this part of the member. Okay, I saved the model. And now, after half an hour, I would say, Rebecca, are there any open questions right now?
No, there are no open questions.
Very good, very good. But now I have another question for you guys. And this is for the design supports. And I have a statement here. I just read it out and then I will send you the question. So the statement is, for the verification pressure perpendicular to grain direction, design supports must be defined. So are they a must or not? Is the statement true or not? Okay, so far so good. Majority have answered. I give another 3 seconds. 2, 1, and I close the question and send you the results. This is very, very good. It is true to have this design check. Pressure perpendicular to grain direction, you definitely need the design supports. Good. Let's go back to RFEM and to our third example of the day. This is just empty model with some base data in it. And now I will show you a Duopitch roof modeled by one single member. Okay, I go to the bottom line just to have my working grid visible. I set it to the XZ plane, and I also want to have my origin of the axis system visible. So that's good. That's what I want. I will set a single member, just using the simple one. It will also be a beam. And now under section, I go not to distribution type uniform. You have those different kinds of tapered beams. Maybe you have used them before, maybe not. You can use a linear tapered beam, for example. And now for my saddle distribution, this is the ones I want to use. Maybe such a fish belly distribution. If I go to the alignment, this can be eccentric or at the bottom. And that's the kind of saddle distribution I want to use. Make this point K, I want this to be in the middle of the beam, so I set it to 50%. That's here. And I want to use my predefined cross sections. So I say at the start of the member, that's point I in my picture. This is cross section 1. And at the saddle point, that's point K. I want cross section number 2. I could use a third one at point J at the end point, but this should be the same as in the start point. So it's a completely symmetrical beam I want to create here. Okay, there's a preview of our cross section, and the material will be GL24C, just to have a glue laminated cross section here. Go to OK and make this one from the origin point of our global axis system 24 meters long. That's here. And we have our Duopitch roof. Okay, next thing I want to do is I want to divide this member, but not really divide it to have small members, but to have internal nodes. So I use the function right-click members, divide member, n intermediate nodes. I want 5 intermediate nodes, and down there's an option to create nodes of the type on member. I say OK, and you see these blue nodes. They are the intermediate nodes. Okay, so now I double-click on the member because I want to use these intermediate nodes for my lateral supports for my stability check. I go to the design types again. I create a new effective length. And now, since we have this glue laminated Duopitch roof, now there can be lateral torsional buckling, so I have it activated. We can also use different methods for the critical moment, MCR. Usually in timber design, we use the analytical method, but you can also use the eigenvalue method or user-defined. So what is user-defined? I go to my effective lengths, and this is where you need to and enter your user-defined critical moment by hand. This is a very common mistake, to set this one to user-defined and then never enter this user-defined critical moment. Leave it to 0 and you will never fulfill your design check. So I go back to analytical, and then we want to see our nodal supports for the stability check. I go back to my dynamic picture, which I use a lot. And now we have only our nodes 1 and 2, which are the start and end points of our member. But I want to have the intermediate nodes as well, so I set the check and go to this button just to set all the intermediate nodes. And I want to select them all using the Shift button and set a lateral support for all my intermediate nodes. I scroll into the dynamic preview, and there are my lateral supports and also the supports of my start and end point of the member. You can also see that we use these nodal supports for the segmentation of the critical length of this member in the different directions. Okay, good. I say, okay, we have our supports. And say, okay, once more. Okay, next thing is, these supports are only for the stability check. We need real nodal supports for our structural analysis. So like I've shown you before, new nodal support, make this a fixed one at the start point, and my roller in, stop, not too quick, go to apply, so I have the nodal support, and now my roller in X direction on the end point. Okay, this can now be calculated, but at first I need some load cases. So I go to the top, I have load cases predefined, and I will have to enter some loads in these load cases. I go to a new member load, assign to member number 1, that's correct, and in the self weight, I need 1.02 kilonewtons per meter. Go to the direction, global Z direction on true length. I'll apply it. You see the load is now in the load case. I switch to the next one. Also on my member number 1, I can, since I know the number, I can edit it right here. Make it 2.7 kilonewtons per meter, again in global Z direction. Apply and next. Done. Then I go to Schnee, that's the snow load. You can learn a bit German here. And you can also, if you don't remember the correct number of the member, use the picking button and pick it in the model. Snow load is now 3.15 kilonewtons per meter, and we have the global Z direction on the projected length right now. Go to OK and have all my load cases with loads defined. You can again calculate the timber design and get an error message. So what is this? Let's see, coordinates of nodes number 3 and 6 are the same or too close to each other. Okay, we can use the model check, but since I know this example very well, I know the cause of this problem, I say abort and go to table. And you see that the node number 3 and node number 6 are identical. So what happened here? When I created this member with the saddle type cross-section distribution, I created an intermediate node in the middle of this member. Afterwards, when I divided this member by 5 intermediate nodes, I've created node number 6, which is identical to this one, which is locked and cannot be edited anyway. So now I go to this identical node number 6, which is not needed, which is simply duplicated, and I just delete it. That's all I need for solving this problem, because we have the intermediate node in the middle of the member, and we also have our support for the stability design check. Okay, start the calculation once more. Now it runs. Yeah, and now we have our design checks in the timber design. You can see stability check, flexural buckling without compression. You can go to the details, check it, all fine. There's one thing I want to show you here, because for this type of section distribution, you can always get the question, where do I find the point on the member with the maximum of our bending stresses? Because we have a linear distribution in the member, but a nonlinear distribution of the bending moment. So where is the point of the highest bending stresses? Usually, if you have a uniform section distribution, it should be in the middle of the beam, but not with this saddle type distribution. So I go to my design checks on members. I don't want to show an envelope. I want to show the max of selected design checks. I leave out the shear in Z direction. Yeah, and you can see there's a point of the maximum for the bending stresses. I should say for the design checks for the bending stress. And if you're not sure if this is really the exact point, I want to remember you that this is an FEA program. So even these straight members have an FE mesh, which is one-dimensional, but you have FE nodes and you calculate the exact results on those nodes. So what I do now is I go to calculate and set the mesh settings for members. And there we have the member divisions. And I set this to a very, very low value of only 2. Say OK and calculate again, and you will see something strange happening. Because we now have these strange values and a really strange distribution of our design checks. This is due to the very, very coarse FE mesh I have entered here. I make another example of a very fine mesh. Make this 48. This is okay. This will now take a little bit longer to calculate, but not much. And now you can see very nice looking distribution, and you can identify pretty easily the place of the maximum bending stress. So this is maybe now too fine, but always remember the rule from FE calculation that the mesh has to be as coarse as possible, but still as fine as necessary. Okay, another thing I want to show you in my section proof with a double click is that you can check the cut to grain angle if you need this. It's here in the design check details. Good, that's for this model. And I have another question for you. And this is another statement. And this is to determine the location of the maximum bending stress, a not too coarse member subdivision should be chosen. Is this true or false? Okay, I give you another 5 seconds, but this shouldn't be too difficult. Guess you know the true answer. 3, 2, 1. Okay, I send you the results. Oh, I hope I didn't put too much pressure on you, because until the moment I gave you 5 seconds, were more true answers. Yes, the statement is true, because a 2-course member subdivision would be the second example I gave you, where I set the subdivisions to the number of 2, where we had this exact kind of results. So this one I have now is 2 fine. The first one I showed you with the 24 subdivisions would be accurate for this example. But don't forget, this is a job of you as upcoming structural engineers to always have in mind that you need to check the size of your mesh. Good. Now for the fourth and last example of today. Now it's the same again. I have something prepared, some materials, some cross sections, and now I want to model it's a truss member, some kind of lattice truss, but of timber. And I want to show you one thing in the model base data here. Under settings and options, there's the option for member representatives and also member set representatives. So what is this? A member representative is kind of a template that helps you modeling and designing a huge number of similar and basically the same members. So if this check is active, you get another tab, Member Representatives Wizard, where you can assign different properties. The rib flange is not needed here. To group those members into the template. So now we have the basic settings for the representatives, all members of same material, cross-section, line type. Member types, lengths are grouped in this template. You can also use hinges, eccentricities, member supports just to separate them, but we don't need to separate any more than the default setting. Okay, go back to OK. And now we just quickly and easy make this thing work. I set a new single member, which will also be a beam. Make it a cross-section distribution uniform with member number 1 of the material number 2. Yes, that's the correct one. Say OK and start from my origin point, 14 meters in the positive X direction. It's here. You can see already that there's a small red rectangle, a small square, which is the member representative. Okay, now I divide this member with one intermediate node, and this time I really want to divide the member, so this check down here is not set. And now I deselect the model, and you can see these red squares for the representatives. And if I click on the squares, I have all members that belong to that representative selected. And I double click on one of them and I have my members 1 and 2, and I can edit them simultaneously. So if you have a really big model with really lots of those kind of girders or columns or whatever, you just click on the representative and you can edit them all at once. Good. Next thing is I want to select the middle node here and just move it up a bit. So no copy, just moving it in the Z direction by minus 1.8 meters. Okay, so and now this is my upper girder, and now I want to define the lower girder. Just doing the same again, a beam member, this time with my cross section number 2. Say okay. Now I have this lower girder here. And since I want to have my upper girder as kind of a 3-hinge beam, 3-hinge train, I go to my first member, I activate the hinges and set this predefined hinge number 1 at the end of the member. Just so you can see what I have defined here, I go to edit hinge. You can see this is just a moment hinge. If you're a bit confused why these are grayed out, this is because I'm using a 2-dimensional model right now and not a 3D model. This is why we only have our 3 degrees of freedom for a 2D model. Say okay, I have the member hinge. And now I just divide all my members. So I draw a window over them. Go to members divide with this time 3 intermediate nodes and create those nodes of the type on member. Okay. This was wrong. I go back, undo. Just do the exercise again. Right click, members, divide by member. And we want 2 intermediate nodes, not 3. Sorry, this was my mistake. Okay, good. Now I have my intermediate nodes here. And I need them just to fill up my truss with the intermediate members. I go to simple member once again. This time we need a member type truss. I just want to show you when we use truss only N that this member can only take normal forces. But in this example, I use the typical truss member we have, which is kind of a beam member with program internal moment hinges at start and beginning of the member. I go to section and use my predefined section number 3. It jumps to material number 1, which is correct, and say OK. And this is just a bit of quick clicking, being patient so I can catch all my nodes, don't miss any. So this looks good. This is now my truss fully modeled. We of course need our nodal supports. So I do this once again. The gelenkig means hinged. On the start, hit apply, and verschieblich in X means the roller in X direction. Okay, now we have our nodal supports. Good, we have again 3 different load cases. In load case number 1, we use the active self-weight, that's okay. And now I want to apply my member loads. I go back one step. I use my member representatives to apply those loads. So I hit member representative 1. We have our complete upper girder selected, and now I go to new member load. This will be in load case 2, 3 kilonewtons per meter, and we need global set on true length. Apply. Go to snow. Then I say 3.5 kilonewtons per meter on projected length. Say OK. Now we have our load cases. And we can start the calculation. Oops, no, there was something I've forgotten. I have not yet entered my effective lengths. So the program reminds me, and also in the input data, yeah, the objects can be designed, but there's only a section check, not a stability check. That's why we have the overview, no effective lengths assigned. Okay, I will go back to my member representative number 1, double click on the member, and then I can edit my design type. Service class number 1 is correct. I go to this predefined effective length number 1, and I show you in the nodal supports that there's an effective length now given as absolute values. This is 7 meters. You can also measure it out. And yeah, when you uncheck this, you have the length vectors, not the absolute effective length of this member. Okay, I can write a comment, so we can say this effective length is for the upper girder, and I say OK. Next, I go to the lower girder, design types. This is now the second one, still called standard. This is why I edit it and call it lower girder. This is just a simple effective length factor of 1 I have here. Say OK. And OK. And now for the other remaining members, we can again use our representatives. Can select them from the navigated data, just performing a double click on one of those. Go to the design types. And now I say, I edit the second one, copy it, just call it Truss members. Say OK. And now where is it? Okay, that's weird. I say cancel. I have saved it. And now it's here. Okay, so maybe it would have been a better idea to just set a new one and then have it already available. But now this effective length is assigned, and we can perform our stability check. go to calculate. Okay, and now we can see that our stability checks are performed and fulfilled. Good. So I save this model. And I have another question for you, which will be the final one of today, just to see what are member representatives. Okay, till now it is undecided. It's about 50-50. Let's see who's right and who's wrong. It's 40-60. I will close it in 3, 2, 1. Okay, and I share the results. And okay, so 40% of you say member templates with identical properties, and the other 60% say members grouped together like one single member. Okay, I will show you again in the model. When I go to the model base data, when I activated these representatives, you can see the consideration of the member properties for the template we use as a member representative. So the 40% of you were right. This is what representatives are. Now the other 60%, what you probably mean is a set of members. So I have 2 members right now for my upper girder. And what I could do is, if I select the representative number 1, make a double click on it and use these 2 members to create a member set. This is now a continuous member set. Say OK. And now I could use this member set in the Timber design. So I go to parent member set, and I would have to adjust my critical lengths. And so on and so on to treat the upper girder as a single member. But this is not what representatives are. This is a set of members. So that's a big difference. Please have this in mind. Okay, so that's all I have for today. Rebecca, are there any open questions?
No, there are no open questions left.
Wonderful, that's good. I just want to show you our website. Just pull this in so you can see it. I go to the English one. And if you have further questions, you can use our support. You can write us an email. There's a help button down there. When there's a colleague in the chat, you can ask them questions. And under support and learning, you find our frequently asked questions. You find our knowledge base articles to give you a lot of information and background on how to use the program. Okay, that's all. You have endured a long series of trainings, and I say you are fit now for using this in your studies and maybe on your thesis, upcoming master thesis, bachelor thesis, whatever. Say good luck with that. Good luck with your studies. Thank you very much for watching and have a good time and goodbye.